All right, welcome back. We're trying to speed run through Module 4 so that Module 5 we can get to some individual projects and apply like learning objectives to something that's hopefully like what you want to do. Like this is the content that I came for. So today the goal is build and get quiz 4 up online so that Wednesday and Friday we can look at project 4, and then we'll be done with module 4 by Friday and move on to like individual projects for the last 2 weeks. Sound good? All right. Yeah, and the individual, some like engineer, I know as engineers, like you're here because it's like, I just want to know what equation I need to use so that I can plug in numbers and box the number that you want me to box. But this is your chance to like be creative, like try to draw from either work that you've done or clubs or things that you're interested in. So the project is my favorite part. Some people get a little stressed about it. But it's not. It's just meant to show like, hey, I learned something and now I want to apply it in something new. It's a connection exercise more than how do I demonstrate that I can check every box. It's not a big like final project. Cool. All right. So anyway, module 4, quiz 4. What were the concepts and ideas of module 4? What were we doing? Why were we here? Usually I like to do one side of like what was this about, and then the other side what are some examples of problems? Oh, for module 5, yeah. So finish up. Ultimate quiz. Exactly. Yeah, it's like really taking a question and have really taken a place of existence. Yeah, first stage is like what were like concepts Okay, yeah. Collecting. Oh, okay. That's all right. I put it up there so that it wasn't like a blank slate. So I've seen these sort of things pop up. Did I miss any? I think I also saw like kinematic equations. Yeah. 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 Yeah, so you're just taking like the horizontal, it's like you're taking the vector and splitting up the x and y. So I've seen these kind of concepts, and there's a direct connection between these somehow. If I want to change potential or kinetic energy, how do I do that? Like, what is the definition of a change in energy? Work? Yeah, so here, like, these two, I can either say like potential energy change, so work was done, or I can say like work was done to change kinetic or potential energy, right? Like there's always a connection because it's the same exact units. Energy is a joule, which is a Newton meter. Newton meters is force through distance. It's also a Newton meter times rotation, so like torque through an angle is work done. So like motors can add work by saying like this motor applied torque through 360 degrees, so it's 2 pi times torque. It's joules put into the system. All right, so then that leaves momentum. How do I change momentum? What happens? Change velocity. How do I do that? Like what changes velocity? What's the definition of like a change in momentum? Impulse? Force times time. Yeah. So impulse is a force times time. And they're directly connected. If you have a change in momentum, there had to be something that created that impulse to change momentum. And in the back, we were just talking about like these are two tools used to solve problems. You can always go back to, let me create an equation of motion and solve it that way. And you'll still get to like these answers. Sometimes this is like a shortcut. It's like taking the back door of getting you directly to an answer. Let's take a look at that. So here's some kinematic equations, right? At least for one-dimensional kind of motion. Do you remember all these kinematic equations? What are these solving? Because these are all like solutions to a differential equation. What are these solutions actually giving us? Like what does our differential equation look like? Position, velocity, but what about the differential equation? What happens, like when we say F equals ma, what's happening in F equals ma for this, when these are true?
Acceleration is constant.
Acceleration is constant. What does that tell you about force? If acceleration is constant, then since F equals ma, if a is constant, F is constant. So F equals ma, constant, constant. Both of them are constant. I'm doing a quick like derivation. I'm not like deriving like what is work in the sense of, but when we look at these kinematic equations, all of these are giving us either position in time, velocity in time, or velocity in position. Which equation is a work energy equation? Like if I create a work energy equation, what is the kinematic equation that it's going to give me? Constant force. It's just a constant force problem. Which one is it going to give me? What do you think? I apply a constant force and I use work and energy to say this is my change in kinetic energy, so this is my This is the end result. This is how I can solve something. Where do I end up? The v squareds, yeah. Yeah, that weird one that we like almost never use for the kinematic equation, because you can't remember, is it a 2 on the left side? Is there a 1 over? It's like, what's going on? You can always get back to that equation with conservation of energy. Because if I turn the left side into just multiply by 1/2 m, I have 1/2 m v squared minus 1/2 m v0 squared. What's that? Change in kinetic energy, right? So a change in kinetic energy is 1/2 m times 2a is now F, because F equals ma. So F delta x. What? So F delta x is a change in kinetic energy. Kind of cool. So that is our work energy, at least for if your force is constant, right? So if you have a constant force, you're going to end up with a kinematic equation that is constant acceleration. Which kinematic equation do I get for impulse and momentum for a constant force applied? Where do I end up? Bottom left? Makes sense, right? Probably not the first one, since we're only dealing with like velocity. So if I say mv equals mv0, so momentum equals momentum plus ma, which is now F again. This is F delta t. So F delta t is a change in momentum again. And again. So the shortcut of like which method do I want to use, at least if you think you can, if you think you don't need like a full differential equation and going through all of that work, like if you're just trying to get some numbers of like what force is it, or how fast is this going, how much, like what spring constant do I need, the shortcut is that impulse momentum is always velocity as a function of time versus work and energy is always velocity as a function of speed. I'm saying velocity, but really it's like speed, right? Like speed as a function of position.
In that second equation that you just did, when you multiply the m throughout the equation, why does the t turn into a delta t?
So this one is really saying, I used a delta t there because this is saying like t, like an acceleration from 0 to t seconds. So I just put that delta t in to say it could be any amount of time for a constant. Yeah, it's not that the m created a delta, it was more just to bring it back to impulse momentum is always F delta t. And if it's a constant force, then ma was constant the whole time too. Yeah. And so the nice thing about this, at least if you're like, oh, this is just, let me just always use kinematic equations, but these are giving you this equation and this equation is always true even when force is changing. So even if you have like a big force that tapers off, you can still say the work is equal to a change in kinetic energy. But you can't do that with a kinematic equation if your acceleration is not constant. But anyway, did I miss any? These were the main things that I saw. And it seems like we captured a lot of what we were doing, but did I miss anything? Nothing that you want to admit, at least. No. I think the only extra thing was just looking at like angular momentum and defining that. Looking at those kind of problems. But yeah. Yeah, the change in angular momentum is whatever applied moment there is. And we looked at the case when h was 0, and then also from another perspective. Did you already have ideas for examples or questions you wanted to share? I'll take a look around, see where people are at, and try to grab examples or questions to demonstrate like what I'm interested in. Yeah. Okay. Yeah, looking at like different stages. Yeah. Where things like energy is out there. Yeah.
Problem, or like you have that swing thing underneath, kind of, you know, you have to kind of shift the frame for it as well.
Yeah. Which one? Where are we looking at like the moving ball on? Yeah, ball on spring. Yeah. Yep. I like that one. Yeah. It's kind of cool to think about hanging in some frames it's conserved and others it's changing. Yeah.
What is like that? Trying to figure out when you can apply certain modes. Yeah, I like it because it takes like a hard problem and split it up into a lot of projects.
We can go back to things are very different. What questions are involved? Yeah, so very nursing how we're doing the project. Oh, rollers. Is there true things that happen? How the constitution energy changes, potential stuff. Yeah, I like to look into participation
Yeah, trying to bring it.
Yeah, and how seems everything you said, it takes it, it sounds very complicated, and kind of simple, it takes it, it's like a really strong Delta T,
Yeah.
kind of like a single physical.
Yep. Yeah, like if you go back to like the definition of what is
Yeah.
change.
Exactly, yeah, and it sounds like a thruster and a rocker still,
Yeah.
in respect to speeds, but then there's.
Oh, okay, that's fine. Okay. Yeah.
Yeah, I couldn't make
Okay. There.
Yeah.
All right, so here's something. This one came up. A couple of people were saying like, oh my God. That this was kind of like an interesting example of like looking at the ball rolling off the ramp and then falling off the table. And so we've done like that problem. What else would be like a similar approach? Like where else would this come up? Yeah.
Oh, I thought it'd be interesting if after the ball rolled off the ramp, it hit some sort of like a spring or a damper, and then there would be some sort of impulse there as well.
Yeah, what would, like, why would you need like spring or damper on I mean, yeah, we can't, like, we're the engineers, like, we can come up with we can build like any kind of springs, dampers, like put an Arduino in there and like start tracking its acceleration, it's a function of distance. Yeah, but yeah, there could be a question about like, how do we pad its landing, or what does padding look like, right? Yeah.
I'm not sure how we would do this, maybe just like use sort of like same principles we use for springs. So if we get a bouncy ball, then like ask how high it bounced after it hits the ground.
Oh, and then yeah, what happens?
Yeah.
Yeah, it's like yeah, one, oh yeah, this was something, I thought this was really cool. And there's a quality control test that you can use for cranberries. So, and I guess you could do it for other, you're looking at me like I'm crazy. No? We're pretty close to Cape Cod, right? We need some cranberries around here. But like, I guess cranberry should be red. I mean, really, it's like purple. We'll do red. That's all right. Yeah, it doesn't look like a cranberry. It's kind of a weird cranberry. So it was a quality control test for cranberries that there's a wall at an angle, so it rolls down, hits this wall, and bounces off. If the coefficient of restitution, so like the change in velocity of it, is good, it's like nice and plump and round, then it bounces off and it goes into the bin, like the good bin. And then if it's no good, it has like a short bounce and it goes into the trash bin. And it's like a pretty simple idea of just a good cranberry should be bouncy. A bad cranberry is going to be like all soft and gross. So it'll, when it hits the wall, it'll just roll off and fall into the trash bin. Anyway, just thinking about like, how does something rolling off of a table affect like real engineering systems? Like, yeah, it's pretty applicable. You could probably use it for like blueberries. Blueberries would work well. Grapes would be hard. I don't know. You'd have to like pick all the grapes and then roll them, and they're not spherical, so it would roll all weird. But maybe for oranges, this might work okay, or like clementines. Like if you had a whole bunch of clementines, you could throw them all down the ramp, let them bounce off. So quality control. Sorry, what other examples would be like similar kind of all on a ramp problem? Or like same problem solving, but maybe a different setup, looking at something else. Yeah.
You could do like the collision of two objects, like the problem that we did on the homework where the boat was coming into contact with the steel cable.
Yeah, for that, trying to prevent, like, for that Francis Scott Key Bridge, I remember for the next week or two, people were kind of writing these opinion pieces about, like, why didn't engineers plan for this kind of disaster? It's like, well, you can, but it's a lot of tires that you need to strap to this bridge, or it's like pretty big inflatable thing, or a tugboat that's always there, like ready to apply a minute worth of anti-thrust to this thing. It's a difficult design problem to deal with. Yeah, that boat coming in. What else would you need to stop? What's something that like has a big momentum or lots of kinetic energy that you need to like dissipate in a safe way? Like get rid of energy somehow. I know I'm asking you to be like all creative. This is just practice for next week. It's like
Catching a baseball.
Catch a baseball? Yeah. So what happens when you catch a baseball? How fast is it moving when you catch it? 0. How fast was it moving before? 99? Damn, you got some crazy friends. Yeah, usually probably. I mean, at least throwing with like Little League, we're doing like 20 miles an hour usually. I don't know. This is college, so maybe it is 99 miles an hour. So there's got to be some kind of change in momentum, right? How much padding can we put in there to stop the ball? We don't have like a lot, right? I'd say even ½ inch is probably too much. 1/8 inch.
Catcher's mitt's pretty good.
Catcher's mitt, yeah, catcher. If we're doing 99, then now we've got a little extra padding. Catcher's mitt.
We catch the ball, there's like.
Yeah, but I think you need, because you have to plan for the fact that you're not always catching it in the basket. Like I think you have to plan for. Yeah.
The most of padding on the sides on the left part.
Yeah.
Because when you block.
For blocking, you're catching. Always in the net. Always in the. I mean, you're supposed to.
It's just not there.
Yeah. Well, that makes sense because there's also no like bones there if it's in the net. Yeah. So then we're all set. Did anyone else do this experiment in high school where your physics teacher put up a blanket, like, and then you throw an egg at it? Did anyone break the egg? No.
We did it now.
Want to try it? I don't have. Plus, that's like, what am I, a millionaire? Gonna bring in eggs to throw at a.
No, it doesn't. Trader Joe's for 3.
That's pretty good. Yeah.
You just have to get there early.
You just got to turn them and flip them, egg flipping. It's like.
And you could only get one card per person.
Yeah, only one. Yeah, just start frying eggs. $5 a sandwich. Yeah, But main thing is like F delta T is whatever that MV0 is, because we have nothing there. So we can decrease force by increase time, decrease force. But overall, F goes down. So we can increase the time of the impact. So stuff like foam is a great way to just like let it deform even for an extra half a second rather than a millisecond. It's a lot better to stop it. And when you hit when you're hitting the net, what is it called? Of the glove. I don't know what that's called. Web? Web? Web. All right. When you hit the web, really that's like a big blanket where delta T is, I don't know, half a second or something. Like it gives it time to deform. Now F is like a couple of newtons. And that's easy on your hands. Yeah, but if you're always catching in the palm of your hand, and you're creating a lot of vibrations and issues. Big impulses are not good for bodies. Helmets? No impacts for helmets. No football players here? No. No football? Maybe? Any skateboarders? Did anybody skateboard? Or still skateboard? No? Just me? I don't much anymore, but I used to a lot. Mostly like a boneless. I liked the old, because I rode like a longboard, and we would sneak into like drainage ditches to skate most of the time. So boneless I could get pretty well. That was pretty fun. And at one point I was okay at an ollie, which is not like a trick. It's like a starter trick for most people, but it's hard to do. It takes a while. All right, so no skateboarding. Baseball, maybe. What else we got for quiz 4? It is baseball season. Ooh, do you know what the radius of percussion of something is? Speaking of baseball. Radius of percussion. All right. So we'll use the idea of like baseball again. Again, baseball season. So we have MV. Just kind of looking at top down. Oh God, what happened to that bat? So radius of percussion is where is a measure of like where the center of mass should be, so that the place that you're holding it has no impulse created there. So a bad radius of percussion would be like away from your handle, but we have like something when we're just looking at the bat. Our ball is creating an F delta T on the bat somewhere there at a given radius. And then we versus like where that center of mass is. Like somehow relate, so you relate like where the impact is and where that center of mass is, and you can change where the center of mass is so that where you're holding that R, the R, the distance to where the impact happens, has a 0 impulse, something like that. So looking at like some of the moments, but some of the moments times time. Radius of percussion. Yeah, we're trying to get R to be like a 0 force radius somehow like that. And that one's good for also like axes, have the same question about like where should the center of mass of this axe be so that when we're swinging it, it's not always like shaking our hands every time we hit something. What else are we thinking about? Check back in. Got a few minutes left. Yeah. I think it would like who does that? That comes up in stuff like if you're loading or like packages, like if you were trying to design like a what's it called? Yeah, like conveyor belt thing. Like in one direction, you're like having packages go down the chute to hit the conveyor belt. You gotta come down, lose momentum on the transfer, but they still have enough forward that they're gonna hit the wall. So how do you design the wall so that it's not just like bending, letting it fly?
Or breaking.
Yeah, or breaking. Yeah.
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 So that's a good example.
Yeah. 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 Yep. F sine alpha. Yeah. Yeah. Mm-hmm. Yeah, so if we look at alpha between the two, R is pointing, if it's directly this way, on the e-axis, R points this way, F points that way, so alpha is 180. Oh, that one's just the general, like if this is the formula you're using, then that is the,
But since this F is actually this way.
yeah.
This is always
That one's always 0, yeah. Because the spring, since the spring's attached to that point, no matter how you stretch it, it's always pointing back at that point. Yeah. That one is not 0, because we have this, like that distance and this distance. So these two, when we take this cross with that, it's still 0. But this 1, 0, t cross with that keeps getting bigger. Keeps getting more and more moment as that thing gets further away.
So it ends up being this, whatever.
Yeah.
These questions are just like I wouldn't know that I wouldn't know where to start with this question. I can follow and I understand how the function is.
Yeah.
Like I'm gonna do this by myself.
Yeah. It was easier. Yeah. Okay.
That one, I was just showing. That's how a lot of people do their cross products.
Well, I don't
Oh,
know.
okay. Well, that's like position crossed with velocity, which is m times that is your because r cross mb is h.
So this is for the same problem. Someone else to use it for
Yeah, like r cross f is r cross ma. So f is the change in r cross angular momentum, just like a letter to say how much spinning momentum you have. Yeah. Okay. Yeah. Okay. Impulse movement done by the other wall. So is it like a horizontal wall? It's stopping it and then it falls down, or does it go up the wall and it's the other side? Okay. Okay. Yeah. Conveyor belt kind of thing. Yeah.
So we could think about, we were talking about like conveyor belts and kind of shipping facilities. I was just driving through Jersey over the weekend. They're like huge Amazon warehouses. I think that's where I was thinking about. I don't know if other people are thinking about Amazon warehouses and that kind of thing. But here we could think about same kind of questions that we were looking at that for that ball rolling, like down the ramp, hits something, now it's moving in a different direction, impulse is applied. That like what's happening to this box, or like how long can you make the ramp versus like how stiff do these walls need to be when the box is coming off of this thing, right? Because it, why did I delete that? Because if this is my H, what's happening to this box by the time it gets to the end of the ramp? How fast is it moving?
Is there no friction? Is there no friction?
No friction. It's usually like on rollers, and the rollers, I mean, if you want to factor that in, the fact that they start spinning reduces, now you're creating kinetic energy in the rollers, like now you have rotational, but we could say they're like pretty small. So they have, I is almost 0, so we could say.
We assume that it's like
ideal, then we could just set up MGH equals kinetic squared.
Yeah. So then the M's go. So we've got V2 is root 2GH. So then what happens at the wall when we hit this wall?
It loses its kinetic energy.
Yeah.
And I guess it only restarts.
Yeah. How much? Like, yeah. So it loses kinetic energy? Do we just say it goes to 0?
It loses the horizontal kinetic. They would just all be vertical.
Yeah, it would lose like whatever is traveling this way, but if it's falling down that way, it still has that. Yeah, so we would have like, that's our new V3, and whatever this Vx, that MV, whatever MVX hits the wall, that would be the impulse that the wall has to apply to that box to get it to change, to stop moving that way, and then go on to the next position. Or like Rube Goldberg machines, they're always big on like moving around, hitting a bell, bouncing off this way and that. All right, we're running out of time. What do we feel like demonstrates our learning for Module 4 and what we're prepared to do? And is like shipping, like conveyor belt work, or projectile motion. We've done projectile, right? Yeah. Elastic, what kind of elastic collision? Yeah. Or like quality control, or like cranberry quality control. I don't know, this is your chance. Energy conservation. Looking at that. Maybe like energy through some kind of conveyor belt system, something like that. Try something like that. All right, we can do that. All right, so maybe this will be some variation. Thanks a lot.